Okay, my name is Twinkle Jain, and today I'm going to present my work on fixing the single point of failure of the ROS master. So as we know that the ROS master is a main component of the ROS framework, and what if it fails, it crashes, the whole system will compromise. So how about we save the state of the ROS application periodically, and whenever it crashes, we can resume our application from the last saved state. Luckily, the DMTCP, the distributed multi-threaded checkpointing system, provides the same thing. But it didn't work when I first tried to checkpoint the ROS application. So there were some barriers. As the talk moves forward, I'll talk about how DMTCP works, what are the barriers I faced while checkpointing the ROS application, and we're going to see the live demo of checkpointing a ROS application and what DMTC has to offer in the future with the upcoming ROS 2 framework. So let's get started. So as we know that what's the core problem is the ROS 1 architecture. So ROS 1 contributes in the major services of the ROS framework, and what if it dies? If it fails, there is no way to recover the system after crash. And the nodes has no way to discover the other nodes, and we need to reinitialize the system. So, as we know that the robotics application runs 24/7, so the amount of loss can be huge. So what are the possible solutions? So we can move to a reliable hardware, but again, it's hardware, it can crash anytime, and it will be an expensive solution. So we can reduce the dependency on the ROS master, but currently it's unavailable in the ROS 1, and it can be applied in the future version, but it's a lot more work to do. So what if we provide an efficient solution which can work along with the current framework of the ROS 1 framework? So it's a checkpoint and restart. So we save the state periodically and resume the state from the last checkpointing. So I hand over Gene to review the DMTCP history.
Thank you. So DMTCP has been an active project for 13 years. There are, at this point, over 10,000 downloads of the source, and we don't know the number of downloads for the binary packages. It's open source, it's free, and we've had a lot of collaborators, both students within Northeastern University and collaborators outside of Northeastern, including collaborators such as Intel Corporation and NVIDIA. It's transparent and it operates in user space, no administrative privilege needed, no root privilege. You don't have to modify your application at all. And in particular, we're working, hopefully by the end of this year, to also be able to support checkpointing when using the NVIDIA GPUs. So the workflow, we don't really have time to go into any detail here, but you'll see some excellent descriptions of the details of how DMTCP works on the web, if you go looking for it. But ultimately, we're just saving the user space memory, and also a certain amount of information about the kernel state. And then we have some magic recipe for also draining the data in the socket before we actually checkpoint. And then similarly, we can do something like that for restart, only in reverse. Notice we do handle distributed or multiple processes. That's really important for ROS because now you have many processes spread across multiple nodes. And so when we checkpoint or save the state, we save the state of absolutely everything, not just the ROS master, but also the various clients. And that way, when we restart and we bring them up again, they are in a completely consistent state because it looks exactly like at the point when they had been checkpointed.
So as I said earlier, when I tried to checkpoint the ROS application, it didn't work. So what was the main problem we faced? It's the pseudo terminals. It's a Linux object, which is a pair of two virtual devices connected with each other as a bidirectional IPC channel. One is master and the other is slave. And the both combined provides, it emulates the real text terminal, which enables you to type into the terminal and gets the produced output out of it. So, so what's the problem? Because it is important to checkpoint PTYs because the ROS application uses it, and the DMTCP was never designed to checkpoint the pseudo terminals completely. So. So the goal was to maintain the state of the ROS application at the time of checkpointing, after the checkpointing, and when we restart the checkpointing, at all places the state should be same. So in order to checkpoint the PTYs, we need to handle the complex characteristics of pseudo terminals. So we need to write the wrapper function of PTYs utilities. We need to see what is the mode. Is it a non-blocking or blocking mode? Is it a row or cooked mode? And also we need to see that what are the terminal settings, how to drain the kernel buffer, and when we refill the kernel buffer, what should be the order? Can we leverage the IPC buffer's characteristics in order to checkpoint the pseudo terminals? Like whenever you write on the master, it appears on the slave. So can you use this characteristics to be able to fill the kernel buffer again? So that's how I sum up the difficulties I had in the pseudo terminals, and this is how the first part is the checkpointing. I'm just showing the PTYs plugin. It saves the terminal settings first and the drain, and again refill the PTY kernel buffer. So in order to checkpoint successfully, and in restart we need to see the order of kernel refill. So I did this timeline to say that what should be the order. You can again see the slides in detail. And let's talk about the live demo of ROS application checkpointing. So in ROS application, we have 3 processes: a ROS core, a listener, a talker. In DMTC, we have DMTCP coordinator. So okay, I'll switch to the core. I don't have time, so I just typed the commands before. So in the 4th window, I'm starting the coordinator, and now I'm starting the ROS core, which will wait, and now it's listener, which like wait for the listener, and the talker. Now we can see that there is a message communication is going on, and now if I type C, or which is the short form of checkpointing in the coordinator, it will checkpoint. So we can see that it is stops at the 10, but it starts again at the 11. So it was successfully save the state. I can kill the processes, all the processes by the type K or kill. So now I need to restart the application with the so I can, okay, so, okay, DMTCP pen, and then DMTCP restart. Okay, now it's a J for joining, P for port, it's 777, and then we have to provide this, what are the, okay, CKPD, ROS core, so it is ROS core, okay. Then CKPD. So it's Python. So okay. So I want to show the one more thing, the ls. So it didn't save just the ROS core or not the talker and listener. It saves the Python as well. We have the Python checkpointing file as well. So it did checkpoint the whole application, not just the ROS master. So we can do the same thing with the DMTCP start. So it's J777 and listener. Okay, we started. It will wait until you start all the checkpoints. And here we go, toggle. So you can see it starts from the 11. So you can see that it works, and we can checkpoint it again if we want to. If we can, now if you want, if we restart the application, it will start from the 21. Okay, let's just move on the slides. So, okay, my bad. Oh. Okay, so DMTCP has the growing number of use cases. It just cannot, it's not limited to the one application. It can be used for the fault tolerance. It can use the process migration. You can live migrate with the DMTCP because you need to save the states of while you are migrating one process to the another host. And it skips the past long startup times. For example, if you want to use the ROS application starting from the 2021, you can just use the checkpoint files, and you are skipping the first 20 counts. And it can use with the debugging. Suppose you are running a 30 days a long application, and on 29 days it crashes. What will you do? You can checkpoint in like every 6 hours, and in last 6 hours you can replay and say what was the bug I am facing. So it can be helpful, and obviously, so the runtime of DMTCP, the overhead is very low, so it can be used in the embedded system as well. So what is the DMTCP ROS2 and the future? What we have to provide, because we know that the ROS2 is like the architecture of ROS2 is completely changed, and it's not centralized, now it's distributed. So can we do something about it? We can certainly make a ROS middleware, a lightweight middleware, which is transparent to user, and it can provide the facility of a fault-tolerant and resilient system as we are providing in the ROS one. And this is also an open source and package, so there is no licensing problem. And in summary, now we can save the state of a ROS application, and it's plugin based architecture, so we can extend it very easily. It can be bundled with the other application package, like larger application package, the corporate one, and the open source one as well. And in the future, we are hoping to work along with the upcoming ROS framework. Thank you. So yeah, this work was also a joint collaboration with our collaborator in the France. Thank you. Yeah.
Thanks so much. So we do have some time for some questions. So if folks would like to come up to the mic, there we go.
Really cool stuff. It's going to be great to be able to restart a ROS master and publishers, subscribers. My question was, when you were restarting your publisher, it went from publishing 19 numbered back to publishing 11. Is there something in the mechanism that is it saving a particular state in time, and how is that determined?
I think it starts from the where it should have started, I guess. After 9, after 10, I press the checkpoint. I initiate the checkpoint, and it starts from 11, I guess.
Oh.
Yeah, perhaps I can add. One of those windows was for a central coordinator, but our central coordinator is stateless. Therefore, the coordinator is not a single point of failure. When we restart, we bring up an entirely new coordinator that reads the image files, discovers the state, and then restarts everything as it existed at checkpoint time.
Okay, thank you.
Great.
Thank you.
Go ahead.
And how much memory does, I wonder how much it scales as you're saving more checkpoints, because ideally you want to have checkpoints like 10 times per second or
Yeah.
or even once a second, just keeping that really last state. Otherwise, it's hard to go back even a few seconds.
So yeah, we know that in embedded system the storage is very low, and so the goal here is to provide the fault tolerance. So we need to just to save the last checkpoint. So we can override the files again and again, and the last checkpoint file would be saved. So in that case the storage is the same as the one checkpoint.
And I'll also add, as you saw in the demo, we checkpoint typically in a second or less. It could be reduced in time even to a few milliseconds if we were to checkpoint to some fast storage. But when you checkpoint to a hard disk, the hard disk is ultimately the responsible for most of the time.
Got it. So could you run that on a cycle, like every cycle?
Yes, sure. There are flags. You can provide the time, 1 second, 2 second, 5 second, and it will checkpoint according to that.
Over on the left-hand side, I guess. Go ahead. Yeah.
Yes, I have basically two questions, but I think they're kind of related. If the process has device nodes open to a piece of hardware, like a camera or something, does it handle that? How does it handle that? And I think maybe related, what about TCP connections to an external host from a checkpointed?
So when we have we gain the initial control to the every process and the thread of application. We also save the connecting socket connections and the device connected. So in restart, we recreate the socket connections, and we add a virtualization layer in between. So there are new socket connections, but the user won't feel it.
But if I understand, I think the question goes one level deeper. There could be state in a local device driver for that camera, and we have to worry about reconstructing that state also at checkpoint time. And in that case, there is no silver bullet here, but we offer DMTCP plugins which allow you to extend the capability of the checkpoint. And within that DMTCP plugin, we have a template where you would save the state of the device driver for the camera at checkpoint time, and then create a new session with the camera with parameters set up to look like it looked at the time of checkpoint.
Thank you.
Okay, before we go to our next question, can I just ask Jamie Martin, to come up and start getting set up so we can, thanks. Okay, please go ahead. Yeah, it's you.
My question is about the size of the checkpoint files. Is it like the virtual memory size of the process in the memory? And specifically, what about the graphics card checkpointing?
Can you repeat? Sorry.
What is the size of the checkpoint file, the memory image?
Oh, it's just a few kilobytes, I guess.
Well, it's the size of the memory image, correct?
Yes, it's the size of the memory image. So the memory image the application uses, it's the same size.
Yeah. And if you checkpoint the graphics card, is it like 12 gigabytes? If your graphics card has 12 gigabytes?
So I think there's the ongoing project is there on saving the state of graphics. I think Gene would be the best person to say about it.
And more than that, we do have optimizations in DMTCP where you can declare what regions of memory need to be saved and what regions don't. So you don't want to save, say, the screen graphics. So that also speeds things up.
Okay. Thank you.
So maybe we could just take the
Okay, yeah, just a quick question from the website, because we're doing the live stream. So is the demo source code available on the website?
Sorry, I didn't get it.
Is the demo source code available on the website?
Yeah, so we still...
Your demo source code.
So yeah, it's available on web, and yeah, it's like my repository. Yeah, it's available.
Okay.
If you just write to us, we're very happy to give it to you. At this time, I don't think it's on the web anywhere.
Okay.
Yep. Yeah.
Thank you.
Thanks. So why don't we thank our speakers? Thank you very much. That was great.